There we go. All right. Well, welcome everyone. Thanks for joining us today. And a couple weeks ago, we did a webinar on remote sensing basics, following up that today with selecting the best imagery. And so I'm Russ Congalton. I'm a professor of remote sensing and GIS here at the University of New Hampshire in the Department of Natural Resources and the Environment, and I'm also the director of what's called New Hampshire View, which is part of a consortium called America View, which is funded by the U.S. Geological Survey to promote the use of remote sensing and other geospatial data in the United States. And so not only am I happy to do this because I was asked to do it, but also it sort of meets the goals and the needs of what America View would like. And so having these webinars out there are, I think useful. So I'm just going to jump into this. So we're going to talk about basically the requirements of what you need to understand to get the best imagery or to select the best imagery for your particular project. So you have some problem that you want to solve, and of course you've got some budget, which most of the time isn't enough money to do what you really want to do. And so you're going to balance or trade off these 5 factors or these 5 characteristics, and I want to make sure that that's what we define today. That's what we're going to spend our time talking about. So given whatever you're trying to solve or whatever objective you have and whatever resources you have, you need to understand these 5 characteristics. What's spatial resolution, what's spectral resolution, what's radiometric resolution, what is extent, and what's temporal resolution. And this describes the remotely sensed imagery, and you can get lots of different imagery with all kinds of varying resolutions, and we need to be conversant in what these things mean. And so the whole presentation today will come down to making sure at the end that you're experts on these 5 characteristics, so that you can talk to vendors, you can talk to your clients, you can talk within your group to make sure that you're getting just the right imagery to meet your needs. Okay, so let's start with spatial resolution. So spatial resolution is what we call the pixel size or the picture element. And not too many years ago, nobody understood exactly what that meant, but these days with computer monitors and especially high-definition television sets, we all, know the difference between those things, and you've probably watched, some sporting event. I don't know, I'm kind of spoiled now. When I go home, I've got a high-def television. I'm a hockey guy, so, you can see the puck crystal clear, and it's beautiful. And, then you go to a hotel, and maybe that hotel, still has, regular television, and you're kind of blown away that you can't see anything anymore. And so that's what we're talking about. We're talking about level of detail. I also like to think of the pixel or the spatial resolution as a cookie cutter. We're getting around the holiday season here, and so you think about it, whatever kind of gets whacked down inside of that cookie, that's what happens. That's what you see. That's what you get. And so it's an averaging process. So if the cookie cutter is a large cookie cutter, then you may have a mixture of things. And so you think about it, if the pixel comes down in the middle of a large forested area, then you're going to get lots of pure pixels of forest. But if the pixel comes down, maybe around your house, you might get the roof of your house and sidewalk and maybe your driveway and maybe your part of your garden, or whatever you have around your house. Okay, and so then it's becoming a mixture, or sometimes we call that a mixel instead of a pixel. It's a mixture of those different responses, the wavelengths that are being sensed by that particular sensor. Okay, so depending on the size of the pixel, you may get different mixtures. You may get different things that are pointed out. And so historically, digital data, satellite data, most remote sensing data that wasn't photography had very large pixels, and the detail wasn't great. And so if you look on this particular slide, you can see that Landsat thematic mapper, which is the 2nd generation of Landsat satellites, has 30-meter pixels. Okay, so a pixel is 30 meters, think about a football field. You can see that it's showing that it's, almost 30 yards by 30 yards, a fairly large area, okay? Old Landsat MSS data that we talked about last time with 80 meter pixels. The weather satellite data that we see on a regular basis tends to be 1 kilometer or even 10 kilometer pixels. But in the last 15 years or so, we've moved rapidly towards greater and greater pixel sizes, smaller and smaller pixels. And so you can see here spot data, which is a French satellite, having 10 and 20 and even 5 meter pixels. And then you can see some of the commercial satellite data that is being collected these days. And we're getting down, actually, I think we're about at 32 centimeters now as the highest digital data that we're collecting, not from an airplane, but from a satellite. Okay, so pixel size. And so it's important to kind of get a real feel for that. So here's, some slides related to that. So this happens to be Marin County over in California by San Francisco. And this is actually the Golden Gate Bridge right here, and this is the town of Sausalito. Some of you may have been here before, and then you go out here and out to Muir Woods in that area. So here's Landsat data, 30 meter pixels on one side, and on the other side we've got 1 meter digital camera data, so much higher spatial resolution, the ability to see lots more detail. And depending on the application, depending on the problem that you're trying to solve, the 30 meter data might be perfectly fine for you for some reasons, and otherwise, nope, I don't need that, I need much more detail, and so the 1 meter data may be what you need. And so again, we'll talk about costs about this later on, but typically the higher the spatial resolution, the higher the cost of the data as well. And so we'll look at those trade-offs as we go through this. And what I've done here is I've zoomed in a little bit on the area, okay, and so still on the Landsat data I can tell the urban areas are white, and I can see the vegetation, I can see the road going through here, which is a fairly major road, but I can't really distinguish much more than that. But if I look on the 1 meter data, I can see the boats in the marina there, I can see almost individual tree crowns, I get lots more detail. And so everybody said, well, I really want the detail. Well, there's, again, cost trade-offs, but there's also so much more data that's there. So processing of that data, there are many, many more gigabytes and, sometimes even terabytes of data in the high resolution that you may cost you a lot of money to do the processing, or certainly a lot of time to do the processing. So again, there's trade-offs there. But, more examples. Here we go, 30 meters, really zoomed in. So you can see those individual pixels, right? You can see those squares, those cookie cutters. And then here's the 1 meter data. And so, obviously if you wanted to count the number of boats in the marina, 1 meter data would be necessary. You couldn't do that at all, with the 30 meter data. Okay, so spatial resolution. Here's another example. You look at this in 30 meters and you go, well, this is a very small area and I have no idea what that is. There's something going on here. There's some shape in the center with the white pixels, but again, you're seeing the individual cookie cutters. And again, remember what we learned last time, there's information, there's a spectral response for each wavelength of light or electromagnetic energy that pixel is sensing in, and we can graphically look at that. We can do all kinds of things mathematically and on the computer with that, but here we're just visually looking at spatial resolution, pixel size, 30 meters, so like Landsat, 20 meter, okay, we're getting a little bit more detail in there. There's clearly something in the center, but I'm not still sure what it is. And then I get down 10 meter pixels, okay, so I'm seeing that almost looks like an oval or something in the center there, and then, or maybe almost like a donut, and then there's something maybe in the center of that, and then 1 meter pixels, okay? And now it's, clear what that is. This happens to be the football stadium at the University of Wisconsin, and then, some of the other athletic buildings all around that. And you can still see the pixels here. You can still see that it's, it's not perfect. 1 meter data is not, the best. You can get a lot better than that. But obviously you can see a lot more with 1 meter data. So spatial resolution, the amount of detail, the size of the pixel, and very important that we understand that. Okay, so here's some examples of some imagery that we would typically use. So this is IRS imagery, which is Indian remote sensing imagery. And this happens to be called WIFS data. And there are 180 meter pixels here. Okay, so you can see this covers a very large area. And you can also see that, sorry, my phone started ringing. You can also see that you can see Italy, you can see Croatia, you can see the Adriatic Sea there. So you can see lots of information on here, but not a lot of detail. So it covers, a large area, but it doesn't, not a lot of detail. So there's some advantages to that, and we use this kind of information more for continental or large area coverages, global types of things. Okay, and then here we've got some 5 meter data. Okay, so this is Indian remote sensing data as well, but this is a different sensor, and so we're talking about some panchromatic, so some black and white imagery, 5 meter data, and notice this rectangle here. We're going to zoom into that. Okay, so now here's some 1 meter data. Okay, this is Ikonos, which is a digital satellite that's up there now, and was actually the first high spatial resolution satellite launched in 1999. And so you can see lots and lots of detail. You have to be careful what you do in your backyard because people can see that pretty clearly on that kind of imagery. Okay. So here's the same kind of example. We've got starting with the 80 meter pixels, and you can see, in this particular area, there's only 16 80 meter pixels here, a little 4 by 4. But when you go to 40 meter pixels, you can see that it doesn't just double in size, it quadruples, right? And so you can see the amount of imagery, the amount of data that you would have to start encompassing. And so you can see it goes from 40 meters to 20 meters, and even at 20 meters you're not really getting much detail. At 10 meters you can start to say, okay, there's some white things on here, and maybe those are houses, and see maybe some signs of the road. When you get to 5 meters, you start to feel really more confident about that. And then I've even got an example here down to 0.5 meters, so half a meter, 50 centimeters, and you can see lots and lots of detail on that. Okay, so spatial resolution has to do with the amount of detail, and often there's trade-offs, and again we'll talk about that in a second. Okay, so spatial resolution. Now we're talking about spectral resolution. So spectral resolution has to do with the wavelengths. So remember, one of the powerful things about using remote sensing is that we can sense in wavelengths beyond what our eyes can see. So if you look on this little slide here, you can see what the human eye sees, a very small portion of electromagnetic energy, okay, just blue, green, and red. AVHR happens to be the weather satellites, okay, so you can see that the weather satellites don't even see down into the blue portions of the spectrum, but further out into the what we call the near-infrared, and then up into the thermal or the heat portions of the electromagnetic spectrum. Then we get to that first Landsat satellite that's been around since the 70s, and we're talking about green, red, and near-infrared, and we talked last time about the benefits of looking in the near-infrared portion of the spectrum and the fact that we get vegetation stress detection in the infrared portion of the spectrum long before we can see it visually. Okay, and then we got Landsat Thematic Mapper, second generation of Landsat satellites, and we talked again last time about this. And you can see that we've got blue, green, red, near infrared, a couple of middle infrared wavelengths, and then into the thermal. So the nice thing about Landsat Thematic Mapper is that it's got really strong spectral resolution. It senses in wavelengths way beyond what our eyes can see, and quite a number of wavelengths, 7 in this particular case. And so, yes, we saw that those 30-meter pixels, well, maybe that's not as much detail as we would like, but it sort of makes up for that a little bit with the ability to sense in these different spectral regions. Typically, the high spatial resolution data, that Ikonos data and some of those other really high-resolution satellites, especially if you go out to like a Google Earth product and you're zooming in on an area, you will get the blue, green, and red portions of the spectrum and probably the near-infrared, but you won't get these other wavelengths. So typically there's a trade-off between that. Now that's changing as we speak because more and more people are interested in going into these higher different wavelengths, and so we are starting to see some high-resolution, high spatial resolution sensors being developed with more spectral resolution, and so that's a good thing. But most of the high spatial resolution data collected over the last 10 years or 15 years has not had the same good spatial resolution as Landsat and other satellites have had. Okay, so here's why this is so important. Okay, on one side there you see a panchromatic image, and probably you've immediately recognized that at the bottom there as the pentagon right here. Okay, and notice that there are 2 fields that are here. And you look at those fields, and in panchromatic or in black and white, you don't really see anything going on in those fields. Okay, but this is high spatial resolution data, lots of nice detail. You come over here to the multispectral data, and we've lost some spatial resolution. Okay, maybe this is 5-meter pixels and this is 20-meter pixels. I'm not exactly sure, but you can still make out the pentagon, right? But look what happens here. Okay, because of our ability to deal with color, okay, and the fact is that our eyes can only see about 200 different shades of gray, but about 200,000 different colors. And in fact, your computer monitor is capable of displaying 16.7 million colors simultaneously. And we'll get down to that in a little bit when we start talking about radiometric resolution. So hold on to that if you've got questions about that. But anyway, remember, we can see lots more colors. We can distinguish lots more colors than we can gray. And here's where we have this near infrared coming in, and so we can see that this field is actually healthy and growing. That's why it's this magenta color, whereas this field hasn't been planted yet. It's fallow still. Okay, so if I visibly look at that in the panchromatic, I don't see any difference, but I've traded off a little spatial resolution to have a few more wavelengths. When I have those additional wavelengths, I can make what I call a color composite. When I make that color composite, I can now see that something unique is going on in those 2 fields. Even though it's fuzzier, it's not as detailed as the higher spatial resolution data that was panchromatic. Okay, so hopefully that's a really powerful example of what we're talking about here with the trade-off between spatial resolution and spectral resolution. Okay. So here's the same example for Landsat. So as I mentioned, Landsat has very nice spectral resolution. It's one of the most powerful things about it. And so on the top here are the individual Landsat bands. Okay, so the blue band, the green band, the red band, and then wavelengths we don't understand very well, or at least we don't have experience because we don't see them, but as remote sensors we learn to understand them pretty well. And so we've got the near infrared, 2 middle infrareds, and then a thermal band. And again, the same power as I just talked about with the ability to see in the infrared, as I mentioned earlier. Okay, so we can only look at 3 wavelengths of light simultaneously because there's only 3 primary colors. Okay, and so a computer monitor or a television screen is called an RGB monitor. And you might think, well, that's pretty fancy. What's RGB stand for? Well, it simply stands for red, green, and blue. Okay, so don't be fooled by that. And you can only display 3 bands simultaneously. So a sensor like Landsat may sense in 7 bands simultaneously, or another sensor may sense in 200 different wavelengths simultaneously. We can only visibly display for our eyes to see 3 of those simultaneously. And so if I choose to display band 3, 2, and 1 through the red, green, and blue, where band 3 is this one here, the red, band 2 is this one here, the green, and band 1 is this one here, the blue. Okay, so I've displayed red, green, and blue through the red, green, and blue portions of my computer monitor. I get what looks like a natural color image, or what we would expect our eyes to see if we were looking down from above on this particular image. Okay, so that's a natural color, we call natural color composite. And if you look in this field right here, this dark area, you really don't see anything going on. However, I'm going to get rid of one of those bands. I'm going to throw out the blue, and now what I'm going to do is I'm going to look in the green, red, and near-infrared simultaneously. So this allows me to look in wavelengths that my eyes normally wouldn't see in, and I make what I call a 4-3-2 composite, again, shine through the RGB, the red, green, and blue portion of the monitor. So band 4, which is near-infrared, is now being shined through the red portion of the monitor. So anything that's red on here means that it has high near-infrared reflectance. And then band 3, which is the red, is being shined through the green portion of the monitor. So things that we normally would see as red are actually colored green on here. And then band 2, which is green, is being shined through the blue portion of the monitor. So anything that we would normally see as green actually comes out as blue on here, like right there. Okay. Now what's really interesting about that is because we're seeing the near-infrared, notice what goes on in this field. We've got these nice little bright red circles which are telling me that the vegetation right there is nice and healthy and doing really, really well, versus the other places where the image isn't so magenta, isn't so red, and as a result we know that that vegetation isn't doing as well. I couldn't see that at all when I just looked in the visible portions of the electromagnetic spectrum, but when I was able to extend my view into portions that I usually don't see in, that became very, very obvious, okay? And so that's the power of having these additional spectral wavelengths, okay? So spectral resolution is really, really important. Okay, so here's another example of that. This is a true color or a natural color composite, okay? So again, bands 3, 2, and 1 through the red, green, and blue, Landsat thematic mapper data of Chattanooga, Tennessee. And so you can see the river here and the highway, and then obviously the city area itself, okay? And that's a natural color composite, what our eyes would see. We can make that false color composite, or that color infrared composite, if you will, where we now look at, instead of 3, 2, 1, we're doing 4, 3, 2 through the red, green, and blue, and all the vegetation shows up this nice bright red color, and so we could get measures of vegetation health. But we're not limited just to those. We can do other strange things as well. This is ugly. I don't know. You may like this. You may not like this. I don't know. Very easy to see the differences here between the vegetation and the city. The vegetation is obviously green. The urban environments are this, I don't know, fuchsia, or whatever color you want to call that. Okay, and what we're doing here is we're displaying 7, 4, and 2. So we're taking band 7 and we're shining that through the red portion of the monitor. We're taking band 4, again the near infrared, shining it through the green portion of the monitor. We're taking band 2, which is green, and shining it through the blue portion of the monitor. So again, we're limited to only looking at 3 simultaneously, but we can make whatever kinds of composite images we want. Here's another one. Okay, so now we're displaying only the infrared portions of the spectrum. So nothing in here is in the visible, nothing we would really see normally, but what we're displaying is the near infrared and 2 of the middle infrared bands through the red, green, and blue portions of the monitor. And again, you got to get used to this. It takes a little practice, but it's no big deal. And you can make whatever composite images you want, taking advantage of this different spectral resolution of the different sensors that you have. Here's the thermal band for Landsat, and just so you know, on the thermal band on Landsats 4, 5, and 6, it had different spatial resolution. On 4 and 5, it had 120 meter pixels. Okay, so instead of having 30 meter pixels, these are 120 meter pixels. This is measures of heat. Okay, so the city, as you would expect, would be warmer than the vegetation, which can use evapotranspiration to cool itself, and then the water would be the coolest jet, and so that's why the water's the darkest. Landsat 7 has 60 meter thermal band, and then Landsat 8, which we mentioned in our previous discussions together, actually has 2 thermal bands, but it's 100 meter pixel size. So again, you start to become conversant in these things so that you can talk to your clients or your vendors or whoever about these spatial and spectral resolutions. Okay, on to the third one. So we've got spatial and spectral resolution, and that's the ones that people talk about the most. Here's the one that's probably most difficult and the one that most people don't know very much about, and this is radiometric resolution. And radiometric resolution has to do with how the computer works. So we're talking about digital data. So the way a computer historically works is a series of on-off switches, or in what we call base 2, if you remember that from school, or binary language, really just a series of on and offs, or zeros and ones. Okay? And so if you only had one bit of information, okay, just one bit, one bit, that's either on or off, okay? Or in terms of an image, we would be talking about black or white, okay? If you have 2 bits of imagery, okay, then you would actually have 4 choices of what was going on, 0, 1, 2, and 3, okay? If you had 3 bits of information, you would have 8 choices of what's going on. Okay, so if you look at the bottom of this graph, you can see here that historically most digital data came as 8 bits, and 8 bits of information is a byte. And you guys have all heard of bytes, and then you've heard of, kilobytes, and then megabytes, and then terabytes, and then petabytes, and we keep going and going and going, right? So if you have 8 bits of information, base 2 raised to the 8th power is 256, or 2 times 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 2 is 256. Okay, and so that would mean that you would have an 8-bit value, or a single byte of information, which records the amount of reflectance given off by that piece of ground where the pixel is covering for each wavelength of energy that the sensor is sensing in. Okay, so instead of saying, maybe an easier way to think about this would be, is it giving off 0% energy in that one, or is it giving off 50% or 100%? We don't do it that way. They do it in bits and bytes, and historically it's been done as 8 bits or a single byte, and so each pixel for each spectral band has 8 bits of information, or 0 to 256. In a minute, you'll see the power of this. What's happened recently is we've had the ability to expand that. Okay, so if you can do 9 bits instead of 8, then the values, the range of values, instead of going from 0 to 255, can go from 0 to 511. Or if you had 11 bits of information, instead of going from 0 to 255, you could go from 0 to 2047. So you've got lots more discrimination, or ability to tell more subtleties if you have better radiometric resolution. Okay? So here's an example Again, just what I just said, computer storage, 8 bits equals a byte, 2 bytes equals what we call an integer or a word, and then 4 bytes and, whatever. And then I'm just showing you, some binary information there. And depending on how old you are and when you went to school, you may have learned about base 2 or base 8, which is octal, or base 16, which is called hexadecimal. Everybody learned about base 10 because that's what's decimal. That's what our number system is in. But I know when I was in school, we had to deal with all of this stuff. And even on your calculator, you might see a conversion between hexadecimal and decimal or something like that. Okay, so gives you the different intensity levels. So 1 bit, we already talked about that. It's really an on and off. So it's a black and white scenario. 2 bits, 4 levels, 4 bits, 16 levels, all the way up. Okay, and so if you look at the little picture on the side, and this is not as effective typically on a computer screen, but right there it's displaying 16 million colors simultaneously. And if I click on it, it's actually now displaying only 256 different colors. Okay, so not as much intensity, not as much discrimination in there. Okay, now it's only displaying 16 different colors. Okay, so I'm lowering down the radiometric resolution. Okay, and now it's only showing 2 colors. And when we have 2 colors or 1 bit of information, it's simply black or white. Okay, here's probably a better example of what you can see. If you look on one side, it's an 8-bit image, okay, a single byte image, and then the other side there's 11-bit imagery, and you can see that because there's only 0 to 255 intensities here, things can get really bright and kind of get washed out, okay? Whereas if I have 11 bits of information, there's a lot more places, a lot more intensities that can cover that, and so there's a bigger range that I can cover, and you can see that I don't have that same issue there, okay? So that happens for bright areas. It also occurs for dark areas. So again, if you look in the 8-bit imagery, you don't really get any penetration in the shadow here, okay? Again, because there was not enough intensity levels. There were only 256 intensity levels, and there weren't enough, okay? But if I come over here with the 11-bit data, you can see that I can now see the cars in that shadowed area because I have more intensity levels, okay? So that's probably the trickiest one to deal with. And sometimes people will try to fake you out with that, or a vendor may not understand what your needs are. You need to make sure you understand radiometric resolution. All right, extent. Extent is the only one that doesn't have the word resolution with it, and it's probably the easiest one. And extent is the footprint. It's the size of the image. Okay, so weather satellite data like we see on the news every night, covers half the United States at a time, has very, very large pixels, like I said already, 1 kilometer, sometimes 10-kilometer pixels. Okay, if we zoom in, here's half the United States, and if we zoom in, here's Puget Sound area where Olympia and Seattle and Tacoma and all that good stuff are. Okay, that's a Landsat scene. So a Landsat scene is a little over 100 miles on a side. Okay? So if we zoom down, take this square and bring it down here, that's the Landsat scene. You can see it covers a large area, again, Seattle and Tacoma and the Olympic Peninsula. Okay? A spot scene, now we're getting increased spatial resolution, right? Remember, spot scenes are 20-meter pixels or 10-meter pixels, but Landsat scene is 30-meter pixels. A spot scene is about a third the size, about a ninth the size of a Landsat scene. So it takes about 9 spot scenes to cover a Landsat scene. And then, if you want to relate that to aerial photography or some of this real high spatial resolution satellite imagery, you can see the size of them here. They're very, very small compared to what's covered on a Landsat scene. So you want to know, okay, how do they chunk this data up? What's the extent? What's the footprint? When I buy a scene of this imagery, what am I going to get for that? And that's what extent is all about. Okay? And so here's a Landsat scene, and you may recognize this as San Francisco. So this is Monterey Bay down here, and San Francisco Bay here, and Marin, the peninsula we were looking at over here, and here's the city of San Francisco. Okay, so this is a Landsat scene, and actually, as we have mentioned previous, in 2008, the U.S. Geological Survey decided that Landsat imagery would be free. So you can actually download this scene or any scene you want of Landsat data for free right now, and that's excellent. Before that, it was typically about $500, $600 for a scene. Okay, so about 100 miles on the side. This over here is an Ikonos image. Okay, Ikonos is a commercial satellite system. It has approximately 1 meter panchromatic data and 4 meter multispectral. It's gotten a little bit better than that at this point. Okay, that scene is about 11 kilometers by 11 kilometers. But that scene also costs over $10,000. Okay, it's a commercial product. Okay, so very high spatial resolution, not as good spectral resolution, only 4 wavelengths, blue, green, red, and near infrared, but also very, very expensive. Okay, so there's going to be a trade-off. There's lots of information that's contained in a Landsat scene. There's certainly lots of information that's that's inside of an Ikonos scene. Okay, what you may do is use the Landsat scene to find your problem areas, because you can't afford to buy, imagery to cover that whole area. It would cost you, $300,000-$400,000 to cover that area if the scenes were even available. And so you may find some problem places on the Landsat data and then go and selectively purchase the higher spatial resolution data where you need it. So hopefully that makes sense. Okay. Last one is temporal resolution. And temporal resolution is just what it sounds like it is. It's how often the sensor passes overhead. So how often can I get an image of my particular area? So if the sensor's in an airplane, you can fly anytime you want to, right? The issue there is if the weather's bad, you've got a ground crew, you've got a flight crew, you've got an airplane, you've got a sensor, you got everything sitting around waiting, and it's costing, a bunch of money to do that. But the real advantage is if I want something, I can get it. So if I've got a flood situation or, some dramatic event going on, I can get imagery as often as I need it. If I have my sensor in a satellite, I only get that data when the satellite passes overhead. And so some satellites are vertical satellites. They only point straight down. For instance, Landsat. Landsat is set so that it only looks straight down, and it passes over the same place. The temporal resolution of Landsat is about every 16 days. So I'm sitting in my office here in Durham, New Hampshire, and if an image was collected today, because Landsat was overhead today, I've got to wait 16 days to get the next one. If I've got a flood going on or, some other emergency, that may not be often enough. So a lot of the newer sensors, even though they're in a satellite, they have some pointability. So we call vertical or nadir viewing, straight down. And so then these satellites have what we call off nadir or off vertical viewing. Now there's a couple of issues with that. One of the nice things about it is that it allows you to get better repeat coverage, because you can point that satellite to look at that same area. Even if the satellite is not directly overhead, it can point a little bit to the side and see that. Two big issues as far as I'm concerned. One, what if I really wanted that vertical image that day and somebody else wants an off nadir image that day? You're not going to get both of them, so how do they decide who gets what? Typically that would be who pays the most or who's the best customer. As a poor academic, I may only be able to buy 1 or 2 scenes a year. Some other person may be able to buy 100 scenes a year or 1,000 scenes a year, and of course they're going to win that battle. The other issue is more of a technical issue, and that is typically I want the imagery from above. I don't want the sides of the objects. And so as the sensor is pointed more and more to the side, instead of seeing the tops of the trees and the gaps between them, or instead of seeing the tops of the buildings and the spaces between them, I'm seeing the sides of objects. And that actually may limit severely my ability to use that data. So you have to be careful. This is one of those really important issues when you're considering purchasing imagery. You need to know whether it was nadir imagery, whether it was vertical imagery. If not, what was the angle, because that may severely limit your use of the imagery. Okay. All right. So we've had spatial resolution, spectral resolution, radiometric resolution, extent, temporal resolution. Okay. So here's just an example again of some Landsat thematic mapper imagery, San Francisco. I didn't want you leaving thinking that Landsat imagery doesn't have detail in it. Okay, so this is again a zoom in of San Francisco Bay Area. This is a false color composite. Initially there was a natural color composite, then it turned over to a false color composite. And these are 30-meter pixels, but there's lots of detail in here. Here's Golden Gate Park. Here's the Presidio. You can see Alcatraz out here. One of my favorite things to point out is I taught for a while at the University of California at Berkeley, which is right there. And right there is the football stadium at the University of California at Berkeley. And I can clearly see that the football stadium has artificial turf. Okay? And that's because this is a color infrared image. If the grass was grass and it was growing, it would be the same color as the surrounding vegetation, but it's not. And so I distinctly see the football stadium, and I distinctly, see what's going on with that. So there's lots of detail on this image. So don't give up on 30-meter data. 30-meter data might be exactly what you need for your application. Okay. Now, if you're in the city environment and you're, covering a small area, yes, you're probably going to want that 1-meter data, or maybe you actually want, 6-inch data flown on, with an airplane. But the key thing here is that you want to be conversant with these 5 characteristics, because it's a trade-off, because it's a balancing act, right? And cost is a huge component of this. And so the higher the spatial resolution, typically the greater the cost. And you need to make sure that you understand these 5 characteristics when you're trying to solve your problem, when you're trying to pick the best imagery possible. So that's it for today. I'm happy to answer any questions that we have, and I'll turn it back over to Leslie to facilitate that.
Thank you, Russ. So everybody, this is your chance to send in your questions. Again, just use your question section of your GoToWebinar panel. There's a little plus sign next to the word questions. You click on that to open up and type in your question into that panel. So we haven't gotten any questions yet. I think that you're very thorough in your presentation, so I think it might take.
Well, good. I've been doing the presentations, these kinds of things for students for quite a long time, and for actually K through 12 kids as well. So
neat.
Try to make sure that I make it as plain as possible. I like things simple, so
yep.
Hopefully they understood what I was talking about.
I think they did. Otherwise, they'd hopefully.
Either that or they all went to sleep.
No, well, actually, I was going to comment. I'll give everyone credit for this since you're all listening to me. I noticed on the dashboard, I have a little dashboard where I get to spy on everyone and whether they're paying attention or not, in the sense that I think it's whether this window, the GoToWebinar window, is at the forefront of their windows.
Oh, yeah.
And I will say that I glanced at it a few minutes ago, and throughout your presentation, it was very high attentiveness, and it still is.
Oh,
actually.
good.
Even though we're just chatting now. Hopefully people are, again, typing in their questions.
Yeah, good.
Yeah, so no, you had high attentiveness as well as, I think, doing a great job of explaining stuff.
Excellent. And next time, just so everybody knows, if you're on, we're going to talk about accuracy assessment on December 4th. So that's a really important topic and near and dear to my heart. So hopefully we'll have lots of people come and listen to that one as well.
Yes, December 4th at 2 o'clock again. Yes.
Mm-hmm. Yep.
All right. All right, I'm going to wait a few more minutes because I know sometimes it takes a while for the questions to actually come in. But oh, here we go. All right. Oh, Tina Graham is just commenting that she's very excited about the accuracy presentation that's coming up.
Oh, good.
Maybe I should unmute Shane just in case. Shane, do you have any comments about what you've seen so far?
Well, it was funny. I was just trying to type in something, but I can only seem to send something to the organizers or the panelists.
Are you in chat? Or
well, I tried. It looks like my chat, like in the questions part, I can't get it, but in chat, I can't. It doesn't seem like I could select to send to everybody. But in any case, one of the comments I was going to make is that these topics that Russ covered are very static in a way, in that they're always things that you have to consider. But as the new technologies evolve, there's always going to be new and different possibilities. But it's always, as he pointed out, it's a big trade-off between spectral resolution, spatial resolution, cost, availability, and sometimes people think that, oh, well, the spatial resolution is great, but they forget the spectral resolution. Or they would say, well, it's wonderful to have an airplane overflight, knowing that if it's maybe raining that day, you can't go, or if the folks who were, who had the plane before you are on the schedule to have the plane took too long, then your flight won't get done on time. So it's always a trade-off, and those evaluations change over time depending on the new sensors that come on the market, but it's still the same sort of back and forth that need to be done. And the other question, or the other statement I was going to say, is that Russ is one of the best people in the world to talk about accuracy assessment. And he will talk about probably some of his background in it, but I'm really happy that we're able to both have these sort of more basic webinars, but also when I first spoke with Russ about doing webinars, for us and also on remote sensing topics, I remember saying, please do an accuracy assessment, because I know that he knows quite a bit about it, and I think it's a bit of a mystery for some. And also, I think if you're a GIS user, you might have seen accuracy assessment for land cover and may not know that much about it. So I think that topic is both useful for people interested in remote sensing per se, but then could also be very useful to GIS users who wind up using a lot of remotely sensed products to understand how people come up with the accuracy assessment process in the first place.
That's great. That's right on, Shane. And also, lots of GIS data layers are simply raster data sets, and so remote sensing is simply a raster data set. So the same techniques that I'm going to talk about for assessing the accuracy of a land cover map could certainly be used on other categorical raster data sets that are simply geospatial data sets and have been. And so unfortunately, not very much has been done in GIS as far as assessing the accuracy of GIS data layers, except probably in the remote sensing side of things. And so hopefully this will be eye-opening to those of you who are more on the GIS side. And I try to keep one foot on GIS and one foot in remote sensing, although I tend to lean towards the remote sensing side. So, but I teach both. I actually teach more GIS classes than I teach remote sensing classes at this point. So, good point.
So Russ, I do have a question from Max, and he says, what type of project would be limited by the amount of money necessary to obtain more detailed images?
Yeah, so I mean, I guess the big thing there is, it seems to me that money limits every project that we do, because we'd always want, we always want as high a spatial resolution data as we can get, with as many wavelengths as we can get, and we, these days what we like is to have it more than once. So we like this multi-temporal analysis capability where, we're not just looking at what happened in one point in time, but we might look at it in 2 or 3 times over a growing season, or over different the winter and the spring, and then what happened in the summer, kind of things. And so, in my experience, every project I've ever done has been a trade-off with money. You got, okay, I've got this much money, and so I'm going to go and say, like Shane just mentioned, what I really think is going to help me here is to have the different wavelengths. And so maybe I'm not going to get the level of detail, the pixel size that I want, but instead I'm going to have the wavelengths that I want. But what I would really like is to have those wavelengths, but instead of at 30 meters, I want them at 10 meters. Well, the only way I would get that at this point, since there's no satellite up there that's doing that, would be to design my own sensor or find a company who had a sensor like that and fly it on an airplane. Right there, you're talking, a lot of money. So, so it's always a trade-off.
Mm-hmm.
Yeah.
Maybe I will mention just since we're hosting this, some of the imagery, at least, that's available from VCGI for free.
Good.
So maybe I'll just make myself presenter again. Oops.
Oh, was I still the presenter?
Yeah.
So everybody saw me as a goalie on there.
We've been playing, yes, we've been looking at here.
So what the heck is that guy doing? So, yep.
All right, let me go instead of my calendar. There we go. So I just want to point out that at our website, so this is if you're interested in Vermont aerial imagery, if you go to our website, click on Data and Imagery, and then Imagery, and you'll see a little list of links to things that are available. So we have the Vermont Ortho program, which is, you'll see VT Ortho in here. If you play, yeah, this whole list is because it's the recent stuff, 2013. This is all, you can tell by the title of the name of the actual imagery layer what the size is. So these are 0.3 meter, 0.15 meter, 0.2 meter, 0.2 meter, 0.5 meter. Panchromatic for black and white. CLIR means color infrared, so that's the 4-band data. Also, and that's all leaf off. If you read the metadata, you'll see that's leaf off. We also have some NAPE data, which is leaf on, statewide. You can see that's 1 meter pixels, color infrared as well as color infrared as well as, infrared as well as color infrared as well as just color. So I just want to kind of point out this is where you look for it, and if you look at the name of the data layer, you can kind of figure out some information about it. You can also go over here and click on more info to get.
Do you have some LiDAR data on your site too?
That is a very good question. So what we have, if you go back to our data, the main OpenGeo data portal and look for LiDAR, you will see that we have a bunch of derivative products from the LiDAR data that's been collected around the state. We have things like DEMs, aspect, hillshade, NDSM, slope. So these are derivative products. The original data, whatever was made available from the contractor, is actually available on a product, which is to say one of the very few things that we sell are hard drives that have either all of the orthophotos on them or the LiDAR data. So you can see all LiDAR data available from VCGI, and this kind of lists what that includes.
Great.
Yeah.
Yeah, and Shane will probably kick in here, but New Hampshire has a similar type of thing we call our center granite, and so we have a catalog like this as well, and you can go out there and find this kind of imagery. As well as if you're interested in Landsat data, you would just go to either Earth Explorer or what's called GLOVIS, Glovis, and right there you would be able to look in anywhere in the world and download any Landsat data that's available. So, and it's all free. So, yeah, and there's the Granite website. So Leslie's way ahead of the time. So
well, I'm not going to try to show you how to get to any LiDAR-related things because I don't use it enough to do that quickly.
Yeah.
But just figured I'd show that to people.
Yep.
All right.
Leslie?
Yes.
I was just going to say the best way to find the data on Granite is to go to download free data and then data download. And then once this comes up, click to layer link, by data category. So the second link down, link from this layer list by data category. So this is, if people are looking for data, this is the best place to do a quick survey of all the data that are available.
And you can see it looks similar to what Leslie just showed for Vermont.
Yeah, little
so.
search results table.
That's the best way if people are new to Granite to just go on and start looking at data. And clicking the little I under more info gives people a one-page PDF that describes the data. So there would be a place to start.
Yep.
Great. Thank you. Okay. Well, thank you very much, Russ and Shane. And in case anybody missed it at the beginning, this webinar has been recorded. Will be posted at the VCGI YouTube page, which you can link to right from the front page of our website. And if you have any questions, you can always email me or Russ if you caught his contact information. And I hope everybody has a great day. Thank you.
All right. Thanks, Leslie. Terrific.